The other thing that I showed last time is that this counterflow, that is, if you look at the control volume, with the corners 1, all the way here, 1, and then 4, and 3. This control volume has an input of Q dot L, a mass flow rate M dot going down, and the same mass flow rate going up in the steady state. And that means, because you can always put everything in a more meaningful box called control volume. And you recognize that only 3 things are crossing the boundary. This heat transfer arrow and the enthalpy flow rate M dot H1 and the counterpart of that, M dot H3. And for this rate of energy transfer to not to destroy the steady state of the red box, it must mean that exiting through the top is a convective flow rate, which is the difference between these two enthalpy flow rates. Let me see, oops, H3 here. Oops, H3. Let me make sure I did not misread my memory again. Another way to interpret the physics from this drawing is that the enthalpy of the stream exiting must be greater than the enthalpy of the stream entering. And that is happening famously in this particular design because on the TS diagram, in the close vicinity of the dome, where you have these two isobars, pH and PL, with the states 1 is here, state 4 is here, state 2 is here, and state 3 is here. This curved line is the throttling from state 3 to state 4. Throttling is a flow at constant enthalpy. So you see on this diagram the orientation of the constant enthalpy lines, including the line for H3 and the line for H1, showing that H1 is greater than H3. This is the inequality that guarantees the functioning of this refrigerator. And now the relatively new steps, because technology is just like any domain of science, evolves or has evolved in steps. Some of them bigger than other steps. And just like with the steam engine or the fire engine, the steps historically have come from, the big ones, from nobodies. They did not come from the most famous professor somewhere. So if this is the punchline up to this point, Then how to generate and maintain an even lower temperature. And the immediate answer is by using a refrigerant, meaning a fluid, with a saturation temperature lower than the one that is happening inside your domestic refrigerator. The fluid there is one of these freons, although these days, decades before this concern about the environment, refrigerants have evolved significantly toward being more environmentally friendly. When I was a student, the fluid was freon. Right now, the so-called march toward absolute zero consists of employing fluids that were historically called permanent gases. Permanent gases because when they were baptized this way, people did not have access to low temperatures to witness the liquefaction of such gases. And those are CO2 in toward colder and colder, ammonia, and then a few others, including, and then nitrogen, and hydrogen, and helium-4. I know really well the boiling point of this at atmospheric pressure 77.4 Kelvin, and here 4.2 Kelvin. And the outlook of the contrivance that I sketched is not changing, except that the drawing looks really strange. It is very, very skinny. T versus entropy. The dome is here in the corner. I exaggerate, but it's that small toward low temperatures. And then the two pressure lines would be extending upward, the so-called pH and PL. And if you imagine stretching your luck with this design, for this design to be operational at much lower temperatures, you run into the that these constant enthalpy lines that were shaped this way around the dome, and by the way, they were shaped this way, they were curved downward only in the diagram space of size comparable with the dome, but at altitudes immediately greater, the constant H lines become horizontal. Why? Because ideal gas behavior is demonstrably represented by enthalpy as a function of temperature only. We write it as dH equals Cp dt. And that means that the higher the temperature, the more perfect the ideal gas behavior, all the way to, let's say, T0 here, where these two states, 1 and 3, would be characterized by equality of specific enthalpy, not inequality. Instead of this, we have H3 equals H1. So this means no luck, actually. It means that in the box that was stretching between these two extremities, I'll still call them 1 and 4 and 1 and 3. The heat leak that's sucked from the lowest temperature cannot get out through the top. It cannot get out because this particular expression in the drawing on the left is 0. The disaster or the challenge is much bigger. If you think about oh, by the way, you cannot have this sort of low pressure stream flow and counterflow with a high pressure stream to stretch from high temperature to low temperature unless the two streams are intimately coupled thermally. This is called regenerative heat exchanger or a counterflow heat exchanger. So there's a heat exchanger in the tall box, and for the stream-to-stream heat transfer to take place, it is necessary at every location necessary for the high pressure stream to be slightly warmer than, so the temperature of the high pressure stream to be higher than the temperature of the low pressure stream. This is a must. And of course, the same requirement applies at the very top of the column, where the names for these two temperatures are T3 and T1. And that means that T3 must be bigger than T1. And that's much worse than the inequality that I erased from the right. This inequality is even more severe than saying, as the red constant enthalpy line indicates, much more severe than saying that T3 equals T1. In other words, to summarize, we have a total control volume I have to make this drawing because now we're at the turn of the previous century. It is the moment of genius appearing out of nowhere that solves the problem. And the total control volume sucks in, allegedly, this heat transfer rate. At the upper end, we have H3 flowing in, and then H1 flowing out, where H3 must be bigger than H1. In other words, you have a freight train that's full, running in counterflow with one that's not full. The net flow is into the box and is due to the difference between H3 and H1. So this counterflow is the same as a convective heat transfer rate. I'll call it due to the heat exchanger. And now you have two heat transfer rates entering the control volume with nowhere to go, meaning threatening the existence of the steady state. this is the kind of drawing that says this machine will not work. Even though you are spending power outside this control volume. All right, so by this time, meaning 1900, thermodynamics was known, in particular the first law. And you have a control volume that's supposed to remain in a steady state with two heat inputs. The other way of allowing this energy to flow out of the box is as work transfer. I'll say by using the two streams to produce power. And it is possible to use the two streams to produce power because one is a place of high pressure and the other a place of low pressure. And between these two, these visionaries, the first was Kamerlingh Onnes. And there's a whole list of them, but this is a Dutch physicist who got the Nobel Prize for it. He was the first to liquefy helium. How about that? Yeah. Anyway, this is the way to vehicle these heat transfer rates out of a box that for which the heat transfer had no exit. And the technique, which I will sketch now in red, is to, in fact, let me draw the box one more time here. This is the counterflow heat exchanger. Then with the mass flow rate is the same on both sides. Here is pH, PL. The technique is to bleed a fraction of the high pressure stream and to expand it through a cylinder and piston apparatus, and then to dump the expanded mini stream, let's call it m dot E, which is the fraction that flows through the expander, to dump it into the low pressure stream at a lower temperature, because that is what happens to an ideal gas during close to reversible and adiabatic expansion. And this was the first design and the crudest. Of course, there's a lot more to show you graphically. I'll do that very, very soon. Except that I have a better drawing to explain what really goes on here. So we have the ambient here, and then the two streams in counterflow. This would be the throttle. We're not concerned with the evaporator. We're simply concerned with the counterflow that connects room temperature with low temperature. And imagine that those two streams are in very good thermal contact side to side. That's the meaning of counterflow heat exchanger. If you take one of these heat exchangers apart, you'll be amazed by how intricate they are. They're like embroidery in copper and such metals. Again, a kind of it's like the fur on an animal that evolved through the decades. And so the direction is this. Obviously, the heat exchanger has the purpose of doing this, side-to-side heat transfer. And the mass flow rate is coming from the top is m dot, and exiting is m dot. And as I just sketched, there is a fraction being bled to the right. It's called m dot e, and then expanded through a cylinder, and then that fraction rejoins the so-called circuit at a lower temperature. If the look at mass conservation now on the road map followed by the fluid. If it's m dot near room temperature, and if the extracted fraction or the expanded fraction is m dot e, then clearly what's left here is m dot minus m dot e all the way to the evaporator. And the same is true here. Coming out of the evaporator is m dot minus m dot e. Here's m dot e, which means that on this low pressure track facing the expander, the mass flow rate is m dot. In other words, the mass flow rate varies stepwise along the heat exchanger. Okay, so this kind of sketch takes us to an equivalent one shown here. So we have a track of this is m dot and m dot. A counterflow it's called a balanced counterflow, where the two sides are of the same mass flow rate of magnitude m dot minus m dot e. Superimposed on something that's kind of strange, namely you'll see what I'll call it very soon. This is the expander. And this particular add-on on the right-hand side vehicles the mass flow rate m dot e. And the mass flow rate does not change through this looped drawing. You can see here that if you put these two white drawings on top of each other, you regenerate the real one. You have, of course, heat exchanger here, heat exchanger here, and here. But because this so-called imaginary duct was part of this one, you have a heat exchanger surface here as well. You can look carefully. If you add this to that, you get m dot. If you do the same all along, you regenerate this drawing. The add-on, this imaginary other slice of bread on a sandwich, is in fact a portion of a Brayton cycle refrigerator, meaning a refrigerator that uses an ideal gas as a working fluid. That refrigerator is treated in the book, but that is not the purpose of this trick that I'm trying to present to you. It is for you to ask what is the connection between these two slices of bread in the sandwich. How do they communicate? What do they do when they're on top of each other? Well, what they do is this. This particular stream, to go from here to here, must be warming up, because this vertical track is the track between cold and warm. So the extracted stream, while at low pressure, is being heated by the balanced counterflow. So we have here a balanced means m dot equals m dot, a balanced counterflow. That heats this small fraction m dot e, but I like to read my own declaration in the opposite direction. The add-on on the right is actually cooling the main heat exchanger. Imagine now the main heat exchanger, which I already made the point that the heat exchanger is for intimate contact side to side. That's synonymous with very good insulation between top and bottom. So this is an insulation. The conclusion that's worth remembering as text is that you have an insulation, then for that insulation to have a cold end that is, according to your wishes, colder and colder, what you have to do to the insulation is to cool it all along. This technique, in other words, now I'm expressing in heat transfer terms the presence of this expander. The expander strikes you with bulk and noise. It makes noise, you know, like all these reciprocating devices. But the effect is a quiet one. And as you'll see in my next drawings, today, even the add-on is quiet, not the way it was in the year 1900. The names to commemorate would be the discoverer of this technique, and then I mentioned his name already, Georges Claude. Just 15 years later, who made the industrial production of liquefied gases something that took over the world. I called him the French Edison, or the Edison who invented his own things. Okay? So, the message from this little story is that the path to so-called not absolute zero, because theoretically that's impossible, but to lower and lower temperatures or to deep cold, path to deep cold is via this technique called intermediate cooling. Intermediate cooling of what? Of the insulation system that separates the object of the game, which is the bottom end, from the world where we live. So the intermediate cooling of insulation systems. The field of cold, just like the field of power, is a let's call it a highly diverse population of contrivances. But in this domain, the space inhabited by any such contrivance has two parts: the one above room temperature and the one below room temperature. I told you the one below T0 is the cold zone, and the cold zone houses everything, including the insulation of the machine. That was the message of my first 10 minutes in this hour. That insulation has many pieces of hardware. One is the counterflow heat exchanger, this one, which I showed you how to provide with intermediate cooling. But there are a few other parts that are complicated and expensive. One is the mechanical support. You have to hold this evaporator with a by means of a, let me draw it here, an arm. You call it a strut, a bar that's strong in tension, but also in bending. It must not start vibrating when the truck runs down the street. And this strong thing, is leaking. And if you don't do anything to it, this leak that starts from the top destroys any chance you have of maintaining the cold end cold. So, intermediate cooling, which you accept as a kind of a piece of folklore, is easily implemented in this case. If this is the evaporator, then the design consists of capturing the so-called or portion of the boil-off gas, a portion of what was I erased it, coming off the surface here, and placing it in intimate contact with the mechanical support. You see that? So that's one classical design for any mechanical support. These days, the biggest contrivances at low temperatures, say liquid helium, are for electrical machines, meaning superconducting windings functioning while immersed in liquid helium. Well, those have to be powered by electric cables. They're also known as current leads. Here's one. There's a motor here, so you have an electric current circulating through. Well, the cable is, now you got two of them. The cables are conducting electricity, but they're also conducting heat. So what I sketched on the left is valid for as a technique on the right. A bit simpler is the design that is in every aerospace application. All these satellites and rockets, they have what's dear is the inside of the capsule. What's extremely cold is the outer skin of the vehicle. If you don't watch out, you end up freezing the innards. And so the insulations in aerospace are highly, highly developed. The meat and bones of the technique is radiation shielding, installing concentric, let's think of them as blades. Blades were, thin, like one ceiling succeeded by another, and they radiation shielding is the equivalent of what you see here for conduction. For a heat current to pass through even one shield, that heat current is reduced significantly. But if you have a whole series, then the reductions are impressive. But they're even more impressive in terms of decreasing the entropy generation rate. If every radiation shield is cooled by contact with this old acquaintance, which is the cold boil-off gas from the evaporator. You see here one idea, and a whole population of designs. Today, all these things are present in the same apparatus. Small, say in a physics lab, or very large. The rest will be kind of up for grabs. I'm not, as always, I'm not sure what I'll present next time, but I'll do my best to entertain myself first.